Alright, so let's do this problem where we have 0.0180 moles of acetyl salicylic acid dissolved in 0.54 liters of water at 25 degrees Celsius. And let's find the pH of the solution. And we're given the Ka for acetyl salicylic acid. It's 3.3 times 10 to the minus 4. So the first thing I'm going to do is set up my equilibrium equation. HA, that's our acetyl salicylic acid, aqueous, plus water, liquid, in equilibrium with A minus, that's the conjugate base, plus H3O plus. And so we're going to do an ice table. So we're going to, we need to figure out concentrations, right? Because we have moles and liters, and we always put concentration in our ice table. So the concentration of HA initially is 0.0180 divided by 0.5400, and that is 0.00360. So our initial concentration of acetyl salicylic acid is 0.0036. We're not going to worry about water in our ice table. Okay, and we have 0 for our initial concentrations of A minus and H3O plus. So we know we're going to lose minus X of HA to form products, plus X A minus, plus X H3O plus. And so at equilibrium, we'll have 0.0036 minus X equals X and X. Okay, so we need to set up our Ka as equal to X squared over 0.0036. I think I've dropped a 0. Minus X. You can always check your sig figs at the end. 3.3 times 10 to the minus 4. And we should see if we can assume X is small. And so to do that, we're going to take our initial concentration of acid and divide it by the Ka. And so we'll have 0.00360 divided by 3.3 times 10 to the minus 4. And we end up with about 11. And so that's much less than 1,000, which means that we can't assume that X is small in relation to the initial concentration, 0.00360. So that means we're going to have to solve the quadratic. All right. So let's set up our quadratic equation. I'm just going to move this down a little bit and kind of start afresh here. So we're going to have 3.3 times 10 to the minus 4 equals X squared over 0.00360 minus X. And so we're going to multiply both sides by what's in the parentheses. So that's 0.0036 minus X. And I'll write it all out for you. Times 10 to the minus 4 times 0.00360 minus X equals X squared. Okay, and we'll multiply through here. 3.3 times 10 to the minus 4 times 0.0036 is 1.19 times 10 to the minus 6. All right, and then we're going to do minus 3.3 times 10 to the minus 4. And I'm going to go ahead and subtract X squared from both sides and set everything equal to 0. So now we've got our equation written in the form of a quadratic, so we can use the quadratic formula to solve for X. And so we'll end up with X is equal to minus B plus or minus the square root of 4AC. Oops. Nope. b squared minus 4ac all divided by 2a. See, this is why I don't do this very often. All right. So in our equation, a is going to be equal to minus 1, because that's the coefficient in front of the x squared. Oops, and I forgot my x here. B is going to be equal to minus 3.3 times 10 to the minus 4. And C is going to be equal to 1.19 times 10 to the minus 6. And so we can plug these values into our quadratic formula. Negative 3.3 times 10 to the minus 4. We'll do plus or minus square root of minus 3.3 times 10 to the minus 4 times minus 1 times 1.19 times 10 to the minus 6. All of that divided by 2 times minus 1. So inside everything under the square root, including the square root, is equal to, let's just do this, is equal to 2.21 times 10 to the minus 3. Okay, so I kind of like to solve everything in here just to kind of make things a little bit easier. And then this is all divided by minus 2. So when we do 3.3 times 10 to the minus 4 minus the 2.21 times 10 to the minus 3 divided by the negative 2, we'll get x is equal to 9.4 times 10 to the minus 4. And when we do 3.3 times 10 to the minus 4 plus 2.21 times 10 to the minus 3, then we end up with x is equal to minus 1.27 times 10 to the minus 3. And we know from our ICE table that x is going to be equal to the concentration of the conjugate, which is going to be equal to the concentration of H3O+. And concentrations can't be negative, so the second answer, that's a minus answer, cannot be right, which means that x is going to be equal to 9.4 times 10 to the minus 4. And we want to solve for our pH. pH equals minus the log of 9.4 times 10 to the minus 4 equals 3.03. And we could also find the percent ionization, and that's going to be equal to the concentration of A minus at equilibrium over the initial concentration of HA. And we're going to get 9.4 times 10 to the minus 4 over 0.00360, and that's equal to 26%. Oh, times 100, don't forget. I always forget. Okay.